speaker, Dr. Mojtaba. He's a data scientist at KNAPP with over 6 years of experience in the financial services industry. And before KNAPP, he worked at ING as a data scientist across various domains, including commercial, people analysis, and financial crime and fraud. He holds a PhD in computational physics and is passionate about conducting research in trustworthy AI and generative AI topics. And today he's given us a talk about uncertainty quantification. How much can you trust your machine learning model? Give him a round of applause.
Well, thanks for the introduction. Hello, everyone. Good afternoon. Welcome to my talk. Today I'm going to talk about uncertainty quantification. More specifically, I'm looking for how I can humanize ML models in a way that they can interact like humans using uncertainty quantification. I didn't expect that I will have a proper introduction, but I will reintroduce myself. My name is Mojtaba. My background in computational physics, data scientist currently at KNAPP. I've been mainly working in financial services. But I've been lucky that I've worked across different domains. And one of the domains that I worked was financial crime and fraud. And this domain brought to my attention that how important is the role of machine learning models in decision makings. Just imagine that if a money laundering transaction will go through without being notified, what would be the impact of it on customers, company, and society? Or you have a model in production that it generates a lot of false positives, then you need to hire an army of people to investigate all those cases. This question is not necessarily for financial crime and fraud. We can extend it to health as well. And imagine that you have a model to detect if a tumor is cancerous or not. So the decision of the model will be very important and sometimes can be deadly. In such cases that the decision of a machine learning model is important, always and often human involved, meaning that there is an interaction between human and AI or your machine learning model. In this particular case, for instance, Bob asked a machine learning model that is this tumor cancerous? And the model responds with a score, 0.8, whatever you like it. This will be very confusing for Bob, because if I compare this interaction of Bob and machine learning model with the two humans, often when we receive a question, we express about our uncertainty. We give some signals that how we are good with our answer or we don't know it. Either you answer it that, OK, I don't know the answer to your questions, or you say that I'm not sure, or you give some alternative approaches that A or B. If I go back to the discussion or the communication of Bob and this machine learning model, if Bob asks a question, is this tumor cancerous, and model output in a score of a 0.8 is very confusing for Bob, because he says that, okay, how confident are you? Here it shows that the importance of uncertainty quantification in transparency of the machine learning model and bringing trustworthiness when it comes to interaction of AI and human. In this case, Bob can make more informed decisions if he knows the certainty, how certain is the model. There is one more problem, though, is that automation bias. There has been a research recently showing that when there is an interaction between human and AI, automation bias will also impact the decisions. And automation bias is, you might have heard of it from the book of Daniel Kahneman, that is one of those heuristics people use their system one to make quick and fast decisions. And in this particular case, human rely so much on models that they forget their expertise. Again, quantifying uncertainty in this case will also help to reduce automation bias. Speaking of uncertainty, especially in machine learning models, then the question is that from where these uncertainties are coming. it can come from two angles, either a data uncertainty or a model uncertainty. Often when we talk about the data, it depends on how we collect data. It can be on the feature side or it can be on the output side. Suppose you need to label some images and there is no agreement between labelers. Then you're going to introduce some sort of a noise in your data. Or there is a natural variability in the data, like collecting data from a machine that has some tolerance error. Or feature space between two classes like A and B is really intertwined and you cannot separate them. Another type of uncertainty is called model uncertainty. It's coming from the fact that you have a very limited data, so the model cannot extract any pattern from that data. Or the choice of the architecture in your model or the assumptions has been made in the model. All of them can contribute to uncertainty in models. How we can measure uncertainty? There are different ways of measuring uncertainty. But here I just focus on two categories, intrinsic methods and post hoc methods. Intrinsic methods like Bayesian approaches or quantum regression, by nature they can produce uncertainty quantification. So it's kind of a built-in feature in their approaches. Post hoc methods are the methods that it's a post-training approaches, meaning that there is no confinement in your model choices. You can take any model you want and you do it some post-training approaches and try to measure the uncertainty. Here I'm mainly focusing on calibration and conformal prediction. Normally, a classifier output a score between 0 to 1. And we might think that a higher score means that higher confidence in prediction. It depends. It depends how much your model is calibrated, how well calibrated. A well-calibrated model means that if it gives or outputs a score of a 0.8, there is an 80% chance that the correct class for a binary classification is a positive. If I put it in other words, it means that if I bring all the cases that the model gives the output of a 0.8, 8 out of 10, the predicted class should be correct. How we can measure that our model is very well calibrated? Just imagine I have a binary classifier, and I will plot a histogram for model scores. What I would do is that I will take my data, run them one by one through my model, collect the scores, and put them in bucket, or basically I will bucketize it. In the sense that just imagine for the case of 0.5, I will collect all the model scores close to 0.5 and count how many points exist in this bucket. I will use this histogram plot to make my reliability diagram. But this time, instead of just counting number of points in this bucket, I will count a number or fraction of positive cases. If a model is very well calibrated, it means that if I take all the cases that model outputs the score of a 0.5, 50% of them being ended up to be positive cases. Why is it important? It is important if your model is calibrated, the model output, you can interpret your model output as a probability rather than just a raw score. Just imagine that communication of a Bob and ML model. If the ML model is very well calibrated and output the score of a 0.8, it means that there is an 80% chance that this tumor is cancerous. Some machine learning models are not very well calibrated. For instance, random forest. or one of most famous one is a deep neural network. Deep neural network are famous having poor calibrated outcome. If you look at it for this case, this is a reliability diagram for a deep neural network. Red bars shows a perfect calibrated output, and the blue bars shows model output. Just imagine just look at the cases of around 0.9. The output of a model is 0.9, but the accuracy is 0.5. It means that deep neural network is super confident about the score, overconfident about the score, but the cases the accuracy is so low. How to read the reliability diagram is that if the model output gives the values below the perfect calibration, means that your model is overconfidence. Your model is generating a lot of high scores, but the number of positive cases is low. Or if the model score is above the calibration line, is underconfidence. Model is giving low scores, but the fraction of positive cases are a lot. How we can fix it? There are some techniques that you can calibrate the model output. You might be familiar with it, like a temperature scaling, isotonic regression, or plot scaling. I'm not going to deep dive into these techniques. I suppose you might be familiar with these techniques, but I'm going to point another thing is that even though I calibrate my model, it still generates a point estimation. I want to go to the direction that I discussed before. We want to make our model like a human. It gives a prediction set, or it gives a prediction intervals, or gives us some offers to us. In order to do that, I will introduce the conformal prediction framework. It's a framework that transforms a heuristic notion of uncertainty into something rigorous. And the main idea of a conformal prediction is that instead of giving a point estimation, it gives a prediction set for a classification case. For instance, for this image, which looks like 4, 9, what you expect from the conformal prediction, it will be a prediction set. Said, I'm not sure, it will be 9 or 4. If you remember, it looks like a human, it's not sure, but offering you maybe A or B. Or in the case of a regression problem, instead of giving you a point, it gives you a prediction interval. The second advantage is a coverage guarantee. So it guarantees that this prediction set covers the true outcome with a certain probability that you want, or a confidence interval that you want. The third thing is that it's a model agnostic. It doesn't make any assumption on the models. You can choose any type of a model you want, and it's just a post-training approach. And distribution free. There is no assumptions on underlying data. How we can apply a conformal prediction to our problem. There is one recipe to conformalize your ML models. It's just one recipe. Based on your problem, there can be some other recipes as well. First thing you need to do is that you need to have a new batch of data. It's called calibration data. There is one important assumption here is that calibration data has to be exchangeable with the training and test data. It is required to hold coverage guarantee. The second step is that you train your model. As I said, any type of a model you like, you can apply and train it. There is one minor condition that this model should give us an estimation of uncertainty. That's the only condition. The third step is that calculating non-conformity score. Non-conformity score, it says that how much in disagreement is model output and the true outcome. If non-conformity score is 0, means that the model output and true outcome are in a good agreement. And if it's a very high value, means that they're really in a disagreement. And during the prediction time, when you have a new data or a test data, you pass it through the conformal model component. What is inside conformal model component? Two things: your model that you trained, and also non-conformity score. And it will output a predictions. It can be a prediction set for a classification, or it can be a prediction intervals for regression problems. I will illustrate how it's going to work in practice. I pick out MNIST data set. And it's a data set that I believe most of you are familiar with it. If not, it's a data set of hand-written digits from 0 through 9. And suppose that I have trained a machine learning model on this data. It's a multi-class classification problem. The aim is that the model will be able to predict what would be the label of the given image. As I said, the choice of the model, it doesn't matter. You can go for any type of a model you like. The second step is that during the calibration, you have already trained your model. And I mentioned that we need to calculate non-conformity score. I will define non-conformity score as 1 minus model score for given image. How it works. As an example, just imagine that I have this image, indicates number 6. I will send it to the model. Model gives me a prediction or score of a 0.8 being number 6. So then I calculate non-conformity score 1 minus 0.8. It's 0.2. Again, low scores of non-conformity score means that we have a very good agreement between model output and a true outcome. And the larger one means that there is a disagreement between these two. OK, we already defined our non-conformity score function. Now we need to do it during calibration, calculate it on the calibration data. And we sort it out from low scores to higher scores. And you can call it from certain to uncertain. Then we compute Q, or calculate Q, as 1 minus alpha quantile of this plot, or non-conformity score. What is alpha? Alpha is our error. I mean, that's the error that we decide to take. Or 1 minus alpha is our confidence. So as an example, suppose I choose the alpha of 10%, 10% error rate, then 1 minus alpha is 90%. Then I'm looking for a Q. I'm looking for a Q that 90% of non-conformity scores fall behind that threshold or Q. That's how I find or extract the Q. So one more time, 90% of my points here, this non-conformity score, fall behind that threshold. That's how I can extract that Q. One more thing to mention, that this alpha is that error rate that you decide or you choose. If you're so risk averse and you don't want to take much of an error rate, and if you go for a low error rate, it means that your Q might move to the right, and you might take in some of the non-conformity scores that not certain. That's the risk. meaning that in your prediction set, you might have a bigger prediction set. If you're supposed to have a 2, 9, or 4 for that image, you might have a 9, 4, I don't know, some other digit as well. During the prediction time, what we do is that we already done our training, we calculate our non-conformity score, and we extracted the Q. What we do is that for the image, for any new image or new data, we calculate non-conformity score for all classes. As an example, imagine that image goes through the model. If you remember, I defined this as a non-conformity score. I know Q already, and I pick all classes that non-conformity score is below that threshold. So model output or non-conformity score for label 0 to 9, and pick out the cases that non-conformity score is below Q. And that's how I will form my prediction set. That 4 and 9 is a part of prediction set. How we can conformalize our classifier. There is a couple of packages. One of the packages that out there you can use is a MAPI. Essentially, you can conformalize your model in a couple of lines. So what you need to do is that just pip install your MAPI package. Here, you put your trained model, a model that you already trained. This option is a method is how you choose your non-conformity score. And this defines what type of a framework you are going to use. The framework I use is called split conformal prediction or inductive conformal prediction, which you have a separate data calibration data. There will be some other also frameworks that you can use. You simply fit to calibration data. That is alpha. We discussed how much error rate you want to take, and this is a confidence level. And during the prediction, if you have a test data, give your alpha, what you get at the end is that prediction from your model and prediction set from conformal framework. So one thing to mention, maybe I need to re-mention it one more time, that 1 minus alpha 90% is important because that's the guarantee. That's the guarantee you put in to make sure that 90% of the time, the prediction set cover the true outcome. There are a couple of other packages out there you can use except MAPI. There are MAPI, it's the most famous one, CREP, and also Punk you can use. If it happened that you write also your code in Julia, you can use the conformal prediction in Julia. I'm also one of the developers in conformal prediction in Julia. Yeah, that's it. I will conclude my talk. Thanks a lot.
Thank you so much for sharing your experience and giving this talk. We have a couple of minutes for questions.
Thank you.
So my question is...
Hi. Here. Sorry. Thank you very much for the presentation. I have two quick questions. So you showed how you would use it for a classification problem. For a regression problem, what would you usually use for this confidence estimate, like the p-value?
No, for regression problem is more or less the same recipe. But the only difference is that how you calculate that non-conformity score. Because here for classification, in order to calculate that non-conformity score, you define it as 1 minus model output. In the regression problem, you potentially can go, I will define it as model output, y predict, minus y actual. That's the difference. Otherwise, that confidence interval, or the confidence that you choose, that 90% and 10%, it's the same as here. Then it will generate for you a prediction interval with that guarantee that you decided to go. If you go for a 10% error, means that 90% of the cases that the true outcome will be in that prediction interval.
Thanks. The second question is, how much bigger is this confidence interval that it estimates for the predictions so that the actual value is within the interval estimated compared to typical approaches such as just bootstrapping?
How much bigger it is, you
Yeah,
mean?
because it's considered more sources of error.
To be honest, I don't know how much bigger it is, but definitely is bigger than, just do a lot of bootstrapping, then plot that confidence interval. Essentially, this confidence interval from bootstrapping is narrower because of the less variance in the data. How much that one is bigger, I don't know. Maybe it's a case by case will be different. Yeah.
Thank you. So I have two questions. The first one is there any way that you can adjust the prediction sets so that they still give the coverage guarantees if you have some kind of distribution shift?
The only way is that at least I can think of it, it's just with alpha.
Okay, but then we're not guaranteed to have...
The guarantee will change then.
Yeah.
The guarantee definitely will change.
And my first question is, do you expect...
One more thing to add, just remember, is with how you define that non-conformity score or score function. That can be also something that might impact what would be your prediction set.
Okay,
Yeah?
makes sense. And for my second question is, do you think that calibrating the multi-class predictions before using them as the non-conformity score should give us tighter prediction sets, or it doesn't really matter much?
You mean first calibration, then apply conformal prediction?
Yes.
So I've read a paper recently that they use temperature scaling and they applied conformal prediction. That paper claims that it gives higher prediction intervals.
Okay.
I haven't experimented with that. I'm just narrating what happened in that paper.
All right. Thank you.
You're welcome.
Hey, thanks for your talk. What are the assumptions on this technique, conformal predictions?
The most important assumption is exchangeability. Means that your calibration data has to be exchangeable with the training and the test data. If not, that coverage guarantee is not going to hold.
So that's kind of like saying there's an IID assumption, no time series data?
Well, yeah, but for time series, there is some sort of a new type of a conformal framework that they manage these assumptions or try to minimize the impact of this assumption. Definitely, MAPI has it how to do it in the time series.
And then from your bio, you're from NAB, right? Oh, from NAB, the bank, right? But I don't know if you're here presenting on their behalf, so I'm just curious what the use case or application is at the bank.
In the bank, not something concrete, I tell you, at the moment. Yes.
Thanks.
You're welcome.
Okay, wait.
Yeah.
I go.
Yeah. Okay. So if you use time series data, is it possible to include time? Because I can imagine the more you predict in the future, the more uncertain you will get just by intuition. How could you incorporate time in that conformity interval?
I cannot tell you that I'm very expert on that, but there is a progressive approach, means that a new data comes, and the new data will be also part of that non-conformity score, that your residuals will be also updated. At the beginning, it may not capture that sudden fluctuation, but after some time, it's gonna capture it because you're gonna inject that non-conformity score for the new data.
Okay, but it will always be the same interval tomorrow and in 100
No, you
days.
can make it adaptive, actually. Okay. There is some framework that you can make it adaptive. It's the same for a classification. There are some approaches that make it adaptive in the sense that some classes can be much more harder and difficult than some other classes. So how you make it adaptive that it can capture, or the coverage rate is basically stays identical between different classes. Because the coverage rate I mentioned is marginal coverage.
Yeah.
It's not a conditional coverage.
Okay, thank you.
All right, thank you once again. One round of applause. And enjoy your break.